This is notes 14.5 for BC Calc, and today we're going to be doing some things that you'll feel a little bit comfortable with because they are a carryover from Algebra 2 and Pre-Calc. But notice we have this differential equation, dp dt is equal to k times p, and we're asked to find a formula for p. And we can divide both sides by p, multiply both sides by dt, and that'll give us p dp, 1 over p dp equals k dt. If we integrate both of those sides, this will give us the natural log of the absolute value of p equals k times t plus some value c. I'll put this as c1. To get rid of our natural log, we'll raise everything to the power of e, which means this will just simply be the absolute value of p equal e to this whole quantity, k times t plus c1. And that can be adjusted to be just some constant. I'll show that in a couple steps here. The absolute value of p would equal e to the kt times e to that c1. This is that constant I was talking about. The e to some constant is just going to be some other constant. I'll call that c2 times e to the kt. And this is going to be either a positive or a negative value, depending on what p is. So we'll make this c just plain old c, and that'll take into account this positive or negative value. Hopefully this looks a little bit familiar to you, but in essence what we're doing in this differential equation is showing that the rate at which p is changing is dependent on what the value of p is, and it gave us this formula, which again is pretty familiar. It's just the fancy way, or the calculus way, of writing that formula had in Pre-Calc and Algebra 2, where we remember that p was the principal, r is the rate, and t is whatever unit of time. C we know is our initial value. Whenever t equals 0. T equals 0, it's going to give us that initial value. We know that as p is increasing, k must be a positive value. dp dt be some positive number here for k times p. Therefore, our rate, dp dt, would be positive, which again means that p is increasing. Of course, p is decreasing, and then k must have been some negative number. dp dt would equal some negative number times p. We're going to work through two sets of problems. They're using the same idea with two different givens. In the first one, we know that the equation for the dy dt is negative 3 times y, and we're given an initial value here. This tells us that we know k from the start. We know from the beginning that k must equal 3. In this equation, we'll just solve. If you want to think of this p as y is equal to p, with this, but y sub t equals c times e to the negative 3t. Given our initial condition, y sub 0 equals 1, we know that 1 is going to equal c times e to the 0, which means c must equal 1. Our equation, now we know what c is, so our equation will be just y sub t equals e to the negative 3t. It's asking us to solve for y sub 2, which is going to be 2 times negative 3 e to the negative 6 power. Let's take a look at the next one. This time you'll see we're asked to find k. We don't know k. We just know that dy dx is going to be changing with respect to y by some value k. We're given initial condition and another condition, and we should be able to solve this. So again, y sub t will equal c times e to the kt. We know that when t is 0, we get a value of 2. C equals e to the 0. Of course, that would mean that c equals 2. Y sub t equals 2 times e to the kt. We still need to find k. We'll use our second piece of information here to solve that. We'll substitute in 1 for t. Set that equal to 6. And then solve it from here. Divide both sides by 2. 3 equals e to the k. Take the natural log of both sides. That means the natural log of 3 would equal k. That's our answer. How does this apply? Well, we're going to be doing some word problems for these. So first thing we'll want to do is be able to translate what they're saying into an equation. And the first one, it says the rate of y is rate of change of y is proportional to y. That means the rate of change, dy dt, is proportional to y can be written as dy dt equals k times y. The rate of change of y with respect to x is proportional to the difference between y and x. dy dx, the rate at which the rate of change of y with respect to x is dy dx, is proportional to k times this difference between those, y minus x. The next one, the rate of change of y with respect to x is proportional to the product of y and the difference between y and 4. dy dx equals k times the product of y times this difference. From the work we did the other day, you can see, or you might be able to see, hopefully you can kind of work through these and see that this one is not going to be separable, this one will be separable. Let's do a couple quick word problems. First one says, the population of a small town with a population of 1,000 is growing at a rate which is directly proportional to the population. The rate is 2.5% per year. So given this information, we can gather that our initial condition, p sub 0, is 1,000 because it has a current population of that. We'll say that that will be our c value. We know that the rate is directly proportional to the population, meaning that dP dt will equal K times P. And they give us the rate. K is 0.025. Therefore, we want to translate this verbal statement into a differential equation. We'll know that dP dt equals, substitute in here, 0.025 times P. We want to find a formula for P. We know that given this, we should expect our equation to be of this form. P equals some constant C times e to the kt. Again, we know K, we know C, so our equation would be P equals 1,000 e to the 0.025 t. We're done. Let's take a look at the next one. And the next one talks about a car runs over a nail. As air leaks out of the tire, the rate of change in the air pressure inside the tire is directly proportional to that pressure. Translate the verbal statement into an equation. Again, if this is going to be proportional to that pressure, we would know that dP dt would be equal to K times whatever P is. Let's find that K if the pressure before the puncture was 35, and after the puncture it's decreasing at this rate. From the information that they gave us, we can see that C is going to be our 35, K is going to be 0.28, and from here, well, actually this would, we can use our equation here to solve that, because this is actually not K, is it? We're looking for K. And this is actually dP dt, and this should be P, our original amount there. So using this equation, we're going to use that to find K. The rate will be 0.28. It is decreasing, so we'll probably want to make sure that that's negative. And that equals K, which we're looking for, times that initial pressure when it was leaking at a rate of 0.28. Of course, divide both sides by 35. We'll get K equals negative 0.008. Let's find a formula for P. Find our formula for P. We know, again, our initial amount, which is C, is 35. And now that we know K, we can go straight to our equation and write the formula for P. P equals 35 times e to the negative 0.008 t. Let's continue on with some other familiar stuff that you've had before. Remember from Algebra 2 and Pre-Calc that we did half-life problems. It was based upon the idea that A equals P, the PERT formula, P times e to the RT. And we know that R is going to be equal to negative natural log of 2 divided by H, or N, I'm sorry. That's 1. And that was our half-life. proportion there. We still know that we're using this directly proportional to problem. Some of you may even remember the half-life of carbon-14 is 5,730 years. Let's review one of those problems. The half-life of radium-226 is given as 1,590. How long will it take to reduce 100 milligrams to 30 milligrams? We know it's going to be based upon this formula. And again, we're just changing it to the way it's shown in calculus books as opposed to the way it's shown in your Algebra 2 books. It's still the exact same formula. From this value, we can find K, which again was R in your Algebra 2 pre-calc books. It's just our half-life. This will be our C, and this is going to be that piece of some T that we're looking for. We're trying to find out what T is. So we'll substitute in those values. 30 equals 100. E to this negative natural log of 2 divided by 1,590 times T. Dividing both sides by 100. Get this term by itself over here. Taking the natural log of both sides, we'll get the natural log of 0.3 equals negative natural log of 2 divided by 1,590 times T. Multiplying by the reciprocal or dividing by that amount, T will equal 2,761.77 years. Next, we have our Newton's law of cooling or heating, depending on whether the temperature, ambient temperature is above or below the actual item. The temperature T of a hot object decreases at a rate proportional to the difference between the temperature of the object and the surrounding temperature, T sub S. Translate that verbal statement into a differential equation. This dt, capital T for temperature, lowercase t for time, is going to equal K times the temperature of the object minus the temperature of the surroundings. That's the difference of the temperature of the object and the temperature of the surroundings. This is actually used to come up with something called Newton's formula, which is the natural log of T minus T sub S, object's temperature, surrounding temperature, is equal to K times T plus some constant C. So when we have something that is cooling or heating based upon the surrounding temperature, we can use either one of these equations to solve for whatever it's asking. In the first example, the room temperature is 60 degrees, so that's the surrounding temperature. So T sub S will equal 60 degrees. We're going to use this equation because you'll see that we have some temperatures given to us here, 100, 90, and 10 minutes. Just to kind of put this in a way that we can follow what we have. I'm going to just quickly make a table for you guys. At time 0, we know we had this initial temperature of 100 degrees of our coffee. At 10 minutes, we know it was at 90 degrees. And we're looking for this time when it's now 80 degrees. So let's use some of this information in our equation. The natural log of that initial temperature, 100 minus the surrounding temperature of 60 is going to equal K times 0 plus C. We're going to use that portion to solve for C. T is 0, 0 times K is 0, so C is just going to equal the natural log of 40, 100 minus 60. The natural log of, we'll use this next temperature, 90, minus the surrounding temperature of 60, is going to equal K times 10, plus now we know C is the natural log of 40. We're going to use this to solve for K. This is the natural log of 30 equals 10K plus the natural log of 40. Subtracting the natural log of 40 from both sides and dividing by 10 will give us K equals negative 0.02876. Now we can use that to find the value T when our temperature is 80 degrees. Go back to our same equation. Natural log of this time 80 minus 60 equals the K value of negative 0.02876 T plus the natural log of 40. We won't go through each one of those steps. It's simple algebra, but we'll end up with 24.094 minutes when we solve for T. Let's do another one just like that. In 16, the glass of orange juice is taken out of the refrigerator. 40 degrees and placed in the 65 degree room. That means the surrounding temperature, T sub S, will be 65 degrees. And again, just to give you a map of where we are, taking the information from here, we've got orange juice that was 40 degrees, and in 1 hour, 60 minutes, we're at 50 degrees. How long will it take to warm to 60 degrees? Same steps we did last time. We'll start with that initial condition, and that is 40 minus the 65 is going to equal K times 0 plus C. Solving for C, we'll get the natural log of 25, capture the value of that. Next, we'll use the next piece of information, which will be the natural log of, now we're at 50 degrees, surrounding temperature of still 65, equals K times 60 minutes plus the natural log of 25. Solving this, K is going to be the natural log of 15 minus the natural log of 25 divided by 60, which this would simplify to the natural log of 3/5 divided by 60. Using log laws and simplifying the fraction 15/25. Now, we'll use that information and our C value to get that T that we're looking for. 60 minus 65 will equal K, which we now know is the natural log of 3/5 divided by 60, times T plus our C value, the natural log of 25. Again, you can easily do the math there to get to this, but this will give us 189.39 minutes, which is roughly 3 hours, 9.039 minutes for us to reach that temperature of 60 degrees. Hopefully this helps you with your homework. Please note some of the problems in the homework will require you to solve systems of equations. We've done systems of equations before and reviewed those in prior units, but remember, if you have two unknowns, you need to have two equations. If you have three unknowns, you need to have three equations. And you can solve by linear combinations. You can solve these by substitution. Calculator is permitted. You can solve those by finding their intersection. Have a good day and enjoy your weekend. I'll see you on Monday.